In today's lesson, you're going to think about 5 different types of chemical reactions. The first kind is called synthesis. Think about when you're synthesizing information, you're bringing lots of information together. So this is what a combination reaction is. It's synthesis, so taking 2 or more simple substances, combining them together to make something bigger and more complex. In general, you've got A and B come together to form AB. These can be elements or compounds come together to make a bigger compound. For example, Na and Cl, they come together to make salt, NaCl. After we're finished predicting a couple things coming together, we'll want to balance 1 Na, 1 Na, 2 Cl's, 1 Cl, so we better double the right-hand side. That messes up my Na balance. 1 Na, 2 Nas, I better double the Nas on the left. Now everybody's happy. 2 Nas, check, check. 2 Cl's, check, check. Here's another one, Mg and O2. If I wanted to stick these two together to make a compound, I'd have Mg and an O. Now think about the crisscross method here. Mg and O are coming together. Mg has a +2, O has a -2. When they come together, that +2 and the -2 cancels, so it's just MgO. So you don't just squish the Mg and the O2. You have to think about the crisscross method. In balancing, 1 Mg, 1 Mg, 2 O's, only 1 O, better double the right-hand side, 2 MgO, and that messed up your Mg, 2 Mg's, better have 2 Mg's on the left. Now you're all set. 2 Mg's, check, check, 2 O's, check, check, you are all set. The next kind of reaction is called a decomposition reaction. That's when you have something that breaks down into simpler stuff. So think about roadkill. You've got something breaking down into separate pieces. This is the opposite of a direct combination or a synthesis reaction. It's the opposite. So one thing breaking down into smaller things. And generally you've got AB breaking down into A plus B. For example, water. Water can break down into H and O. Now H and O are part of those special 7 atoms that you starred on your periodic table that have to exist as a diatomic atom. So H2 and an O2. H2O breaks down into H2 and O2. When I balance, it gets a little tough. 2 H's, 2 H's, fine. 1 O, 2 O's. Better double the O on the left, but that messes up your H's. 4 H's on the left, only 2 on the right. Better double it to get to 4. So 4 H's on the left and right, check, check. 2 O's on both sides, check, check. Here's another one, calcium carbonate. Breaks down into something weird, calcium oxide and then carbon dioxide. But again, one big thing breaking down into 2 simpler things. Doesn't have to be 2 simple elements. It can be 2 compounds. So calcium carbonate breaks down. Let's see, calcium 1, 1, carbon 1 and 1, oxygen 3, 1 plus 2, 3. That one's all balanced. The next kind of reaction is my favorite. It's called single replacement. And in single replacement, what happens is something solo comes in and replaces one of the atoms in a pair, kicking it out. So my silly analogy is thinking about the Twilight series for you Twilight fans. Jacob and Bella have been best friends, kind of lovers for a long time, and then in comes Edward to steal Bella, kicking Jacob out. So in comes Edward, kicking Jacob out to steal Bella. So one of these solo guys comes in and kicks out an element from a pair to pair up with it. For example, copper, it's going to come in and kick out silver. Silver will be alone, and now copper will be in a pair with nitrate. Tricky part for these pairs, you've got to think ionic. You've got to crisscross charges. Silver in this case had a +2, NO3 had a -1 apparently, and then in this example, copper had a +2 and nitrate had a -1. So now when I simplify, 1 copper, check, check. 1 silver, check, check. 2 nitrates, check, check. This one is all balanced for you. Here's a couple trickier ones. So think Edward and Bella, if that helps. Here comes Edward. It's going to kick out Jacob to be with Bella. So potassium here is going to kick out H. Now when H gets kicked out, it's part of that special 7, has to exist as H2. When K comes in to bond with OH, we've got to think ionic. K has a +1, OH has a -1. So those +1 and -1 will cancel, and then here's your H2. When we balance, we have to count everything. 1K, 1K, 2 H's, 3 H's. Uh-oh, 1 O, 1 O. What are we going to do? Well, Let's try doubling up my KOH. This way, I'll have 2 O's, I'll have 4 H's. Hopefully that'll give me something easier to work with. Doubling the KOH made me double the K over here. Now let's take a look at my O's. I've got 2 O's, only 1 O over here, so let's double that. Now I think we're good. Let's see if we did it right. 2 K's, 2 K's, 4 H's, 2 times 2, 4, and then 2 plus 2, 4 H's, 2 O's, 2 O's, we're all set. Here's a tricky one. Let's see if we can predict the ending. Mg is going to come in and kick out H. When H gets kicked out, it has to exist as H2. And then when Mg pairs with SO4, we've got to think crisscross. Mg has a +2, sulfate has a -2. When they come together, their charges cancel with your H2. Let's balance. 1 Mg, 1 Mg, 2 H's, 2 H's, 1 sulfate, 1 sulfate. All set, actually. It's a nice one. Let's try another prediction. Mg is going to come in and kick out lithium. Lithium will be so low and is not part of the special 7 that needs a double. Lithium is fine all by itself. When Mg comes in to kick it out and pairs up with the NO3, we've got to think ionic, crisscross. Mg has a +2, nitrate has a -1, so the 2 crisscrosses, whoop, down there. -1 is invisible. Let's check our balancing. 1 Mg, 1 Mg, 1 lithium, 1 lithium, 2 nitrates here, only 1 nitrate there. We're going to have to balance that one. Actually, tricky question. This reaction is actually not going to even exist. So this is something tricky that we'll talk about in the next slide. In order to decide whether or not a reaction is going to take place, we've got this little chart that tells us how reactive different metals are. In order for a single replacement reaction to take place, the solo metal that's coming in to kick out the pair must be more reactive than the metal already in the pair. So for example, in the previous slide, magnesium was not reactive enough to kick out lithium. The metal that's by itself needs to be more reactive than the other. So this little chart should be helpful. Any metal that's reactive will displace any metal below it. And then any metal at the bottom that's least reactive is not going to be able to replace something more reactive. So this chart is something that will always be given to you on a test, and it's your job to remember that the more reactive ones do indeed replace these if they're in a pair. However, these guys will not displace something above it in a pair. A double replacement reaction is a fun one. This is one where you have 2 pairs that change partners. So you have this exchange of positive ions, so my A and my B are with X and Y. On the other side, the A and the B are with Y and X. It's kind of like square dancing. You're basically just changing partners. So you're exchanging the positives or exchanging the negatives. You're basically just changing partners. Think about square dancing. Oftentimes you'll say, do-si-do your corners, or boys switch partners. You switch partners a lot, but it's always still guy, girl, which is the same general equation here. You always have plus, minus, plus, minus, plus, minus, plus, minus. So we'll try some of these examples. Magnesium carbonate, their partners, plus, minus. HCl, their partners, plus, minus. On this side, they've traded. My Mg, the plus over here, is now with the minus from the other pair, plus minus, and the H plus from this pair is with the CO3 minus from the other, plus minus. So always plus minus, plus minus, plus minus. If I think about these pairs, we do have to crisscross. Mg over here was +2, Cl was -1, crisscross, whoop whoop. On this side, H had a +1, CO3 with a -2, so they've crisscrossed, whoop whoop. Now let's balance. Mg, Mg. Carbonate, carbonate, H, 2 H's here, 1 H there. We better double the one on the left. Chlorines, 2 Cl's, 2 Cl's. All set. The rest is balanced. Let's see if we can predict the ending for this one. Lead has a +2, nitrate a -1, so plus minus. And then with my Ki, K has a +1, I has a -1. So let's trade partners. Pb is now going to be with I. K is now going to be with NO3, plus minus, plus minus. I did have to crisscross charges here. My Pb +2 went whoop, and the I -1 got ignored. And then my K had a +1, NO3 -1, so they just canceled. Thinking about balancing, 1 lead, 1 lead. 2 nitrates, 1 nitrate. Better double that one. 1K, 2 Ks. Better double that one. Now let's check your I's. 2 I's, 2 I's. I think I'm all set. PB, 1, 1, check, check. Nitrate, 2, 2, check, check. K's, 2, 2, check, check. And I's, 2, 2. All set. Last one, let's see if we can predict the ending. Calcium carbonate with HCl. Calcium has a +2, carbonate -2. H has a +1, Cl -1. Let's trade partners so that it's still plus minus, plus minus. Calcium's now with chloride and hydrogen's now with carbonate. If you look at my crisscross, my +2 went whoop with a -1, which got ignored. And then my H went +1, whoop, ignored. And then CO3 -2, whoop, down there. Let's balance. 1 calcium, 1 calcium. 1 carbonate, 1 carbonate. 1 H, 2 H's. Ooh, better double that one. And then check your Cl's. 2 Cl's, 2 Cl's. All set. The rest is balanced. Now the last kind of reaction is called a combustion reaction. There's a couple different types, but it's the same pattern. And this is when you have something that's carbon-based. Carbon is the element that makes up life, living things, that burns an oxygen and produces CO2 and H2O. Think of this as an explosion. I've got something that's living, burning an oxygen, and now it's going to produce carbon dioxide and H2O. So these examples will all look really similar. Something carbon-based, burning an oxygen, producing carbon dioxide and water. Now if I go to balance, I'll see 1 carbon, 1 carbon, 4 H's, 2 H's. Better double my H's. Now check your O's last. They'll always be the trickiest. 2 O's, and then 2 plus 2, 4 O's on the right. 2 with the carbon dioxide and 2 with the water. So 2 here, 4 on the right. So I better double my O's on the left to make it even. Now let's double check. 1 carbon, 1 carbon, 4 H's, 4 H's. And then the O's, 4, 2 plus 2, that's 4. Here's another combustion reaction. Same pattern. Something carbon-based. Add oxygen, and you'll produce carbon dioxide and water. Let's count carbons first. 3 carbons, 1 carbon. Better triple it. 8 H's, 2 H's. Better quadruple it. Now let's check O's. Always leave the O's for last because they're trickiest. 2 O's, and then let's see, 2 times 3, 6 O's plus 4. 6 plus 4, 10 O's on the right. Let's get 10 O's on the left. Just multiply by 5, and then you're all set. So with these combustion reactions, it's the same pattern, something carbon-based, add oxygen, CO2, and H2O as the products. So you don't have to do any crisscross here. In fact, these are always all non-metals. But you'll see the same pattern, carbon-based, oxygen, then CO2, H2O. This idea of an incomplete combustion comes if you don't have enough O2. If you don't have enough O2, you'll end up with CO instead of CO2. CO, that's carbon monoxide, that is something deadly. So if you don't have enough O2, you'll end with CO instead of CO2, and you'll be in trouble. So you'll be told on a test or an assignment if it's complete or incomplete combustion. Most of the time you'll see complete combustion where you have CO2 and H2O as your products. Incomplete would mean not enough O2, so you'd have CO instead of CO2 as your product here.